Well, greetings out there in YouTube land, and welcome to today's part 3 video of our 4-part series featuring the scratch build of a Gibson GA1 RVT amplifier. Since I posted part 2, some momentous news has come our way, and I wanted to share it with you before we continue with our scratch build video. Well, I'm pleased to report that the public plea for information about the elusive GA1 RVT amplifier has resulted in a viewer alerting me to this advertisement from Flipside Music in Denver, Colorado. And as you see, we have here a Maestro GA1 RVT Reverb Echo Tube Amp, which unfortunately was already sold. I'd considered buying it so we could have a side-by-side comparison with the one that I'm building, but unfortunately it was already sold. Let's take a look at some pictures of what a real original one looks like. I think part of the problem with finding one of these is that it's a Maestro GA1 RVT, not Gibson, and apparently if you search for Gibson as I did, you'll get nothing. But anyway, let's take a look at some of the photos. Here's the control panel, and as you can see we have loudness, reverberation, and tremolo with an on-off switch, 2 inputs. It looks quite a bit like our schematic would lead us to expect. Here's from the rear with the control panel. It looks like a little 8-inch Gibson Alnico speaker, sort of like you'd find in a Champ. I think our 12-inch speaker is going to sound a whole lot better. I really can't see the reverb tank in the bottom of the chassis. I assume it's there. Here's that special design Gibson 8-inch speaker and some side views of the cabinet. It looks to me like the cabinet's about the same size and configuration as the 5E3 cabinet that we got from Mojatone for the one that I'm building. And I think the tweed is going to look a lot better, but still I thought you'd get a kick out of knowing that some of these do exist. According to another resource, one was made in 1962, and 321 of these RVTs were made in 1963, and apparently one of them was sold to whoever is offering this for sale, and there's probably another 321 of them out there or in somebody's closet. So I appreciate the viewer that tipped us off to this, and I thought you'd get a kick out of knowing that the amps do exist, but they're exceedingly rare. Although I started out trying to show you every step in the construction of this circuit, as I continue, it's becoming painfully evident that this just isn't the type of circuit that lends itself to that approach. The chassis is rather small and constricted, and to be honest, the circuit is more complex than it appears based on the schematic. For that reason, I would prefer, instead of going through each specific step, which will take probably about 9 more videos, let's just hit some high spots and some sort of general techniques that will work for you doing point-to-point wiring with terminal strips like I am with this circuit. As mentioned at the end of the part 2 video, the distributed ground technique as well as the distributed B+ method are both excellent techniques to streamline and improve your point-to-point build. I think this might be a good time also to address an issue that many of you have expressed to me about the difficulty you have converting a schematic diagram into either a layout diagram or an actual circuit. And the problem is, I believe, that the schematic doesn't look anything like the circuit. I mean, there's not one place here where there is any sort of commonality between the appearance of the circuit and the appearance of the schematic. And I know that that's 99% of the problem you all have, is how in God's name am I going to translate this, which I think most of you now have become to understand and be able to interpret, into this. Okay? If this and this bear no resemblance whatsoever. And the point I'm going to try to make to you is they bear a really remarkable resemblance to each other, but it's sort of like the interpretation or translation of one language into another. We have the theoretical language here of the schematic that shows all the connections. We have here the practical expression of that language in actual physical components and wired connections. That's the real challenge, I think, to doing this. So what I'm going to try to do is show you how this translates into this, and not by going over every single connection and point. But what I'll do is I'll trace some parts of this circuit as they appear on paper, and then I'm going to show you how they appear in here in the wired circuit. And another point that needs to be made is the way I interpret the schematic may be very different than the way you interpret it. And that's the beauty, I think, of point-to-point wiring, that allows actually sort of artistic expression in the way that you organize the components and connect them in a visually pleasant appearing way, but it also is electrically correct. Okay, so let's see if we can accomplish that. If we can, in this video or in this video series, I think we will maybe done more than we have in any of my previous videos or video series. So let's focus on that instead of the connections at either end of that resistor. Okay, let's see if we can't do that. Now let's discuss the construction of the tremolo circuit. We know that it consists primarily of 3 capacitors in a loop that exits from the plate of the oscillator tube, goes back around to the grid of the oscillator tube, where then the signal is created, sent out through the plate, back to the grid, sort of like a dog chasing its tail. But the action of the capacitors and resistor pairs, here's a capacitor resistor, capacitor resistor, capacitor to resistor. The resistors all go to ground, but these will alter the appearance of the signal so that it becomes a sine wave, and the frequency, which is how many peaks there are per unit time, will be dependent upon the values of the capacitors and the resistors in each of the pairs that it encounters as it goes around the loop. And in addition, we see that since the rate of oscillation is governed by the pairing of capacitors and resistors, by making one of those resistors variable, we can vary the speed of oscillation. And in addition, if we put a switch here and either give or deny ground to that variable resistor, we can actually stop the oscillation. So I think it's very helpful to have a full understanding of the circuit that we're going to construct. How does it function, and what are the functions of the different components? How can the, in this case, speed be varied? How can the whole effect be turned off? And I think that this portion of the schematic explains why so many of you have trouble making the conversion from this to this. And that is that whoever drew the schematic included the cathode bias resistor and bypass cap as if it was part of the oscillation loop. And I think in some of your minds you think that this ground for the 3 resistors has to somehow be connected to the bias resistor. It does not. The person who drew this simply took a shortcut. He's drawing one ground here for the bias resistor and bypass cap, and he's thinking, oh, what the heck, let's just tie in our resistor loop to that. In reality, this and this are unrelated. So you can construct your oscillation loop independent, if you wish, of the cathode bias and bypass circuit, and have 2 separate grounds if you wish. So don't think that you have to be limited to the literal translation of what the schematic says. You need to gain enough knowledge of the function of different sub-circuits so that you can see that, well, let's see, this oscillation loop here can function independently of the cathode bias and bypass cap, and therefore not get confused about your wiring. Okay, I hope that makes sense. And all through this schematic, there are confusing additions that have been put in to make the schematic easy to draw. But those concessions to ease of drawing should not confuse you or limit you or prevent you from seeing what's been done. Look at this. A 0.047 microfarad cap from the screen down here to ground. Does that mean that the cathode bias resistor and bypass cap have to be connected to the 0.047 microfarad cap for the circuit to work? Of course not. This and this are 2 different things. The only reason they're connected is to make the drawing easier to create. Now let's see how we can translate this theoretical line drawing into hard-wired components on a terminal strip inside a metal chassis. Step 1, I'm going to do a little thinking on where these need to be positioned, and I'm going to solder them to the terminals right back here. This is the strip that I attached in the chassis, with the idea being that it would be the oscillation circuit for this tube right here, the 6BM8. Looking at the schematic, I see that as we come out of pin 9 of the triode of the 6BM8, we'll go through the 0.03, 0.02, 0.02 microfarad cap. So I look down here, and here is the pin 9, and to me it's really close, which is important, to this terminal. So I'm going to solder the 0.03, the 0.02, and the 0.02 microfarad caps sort of in reverse order. This is a good example of translation. On the paper it's 322, in the chassis it's going to be 223 from left to right, and I think you see why. 0.03 is right adjacent to that pin. See, you have to make that type of an alteration for practicality's sake. So let's wire in our capacitors. So our oscillation loop exits from the triode of the 6BM8 plate, which is pin 9, through 0.03, 0.02, 0.02, and back around to pin 1. Here we have 0.03 to this point right here. We pick up 0.02, come around to this terminal, around here to 0.02 to this terminal. Now to complete our loop, remember this is the 0.03, we're going to come from here down here to pin 9, and we'll go from this terminal over here to pin 1, and we will have our oscillation loop. The final step will be to put in the resistors that are attached in between each of those capacitors. Okay, so let's make these short jumpers here from this terminal to pin 9 and from this terminal to pin 1. Another important point is there was a nut right here holding the output transformer to the chassis surface. I felt that that nut was a little too close to this terminal. There was some chance of a short circuit, and so I used super glue to put a piece of rubberized paper over it, which will insulate it and prevent any sort of inadvertent contact. You have to think from an engineering standpoint, what's the worst case scenario, what could happen, what could go wrong, and prevent it from happening. And I think that's a real good step right. Let's look at our closed loop. We'll go from pin 9 through this brown wire over here to this terminal, through our 0.03 microfarad cap, 0.02 microfarad cap, 0.02 microfarad cap to this brown wire here, comes around, goes underneath the orange drop, comes out over here and connects to pin 1 of the 6BM8 triode. Now we have to add our resistors to ground in between each of these 3 capacitors. Now when it comes to the 3 oscillator loop resistors, we have a problem in that Gibson never gave us a value for this one. This is the resistor that goes to the wiper of the Tremolo speed control. So that will be left to experimentation after the circuit is all finished and the amp is operational. I will use trial and error to come up with the proper resistor value, and I will provide that for those of you who are trying to build this unit at home. Okay, so we'll have to be patient on that one. But these two we're now going to add in. The 1.5 meg will be between the 0.02 and pin 1. The 510K will be between the 2 0.02 microfarad caps, and as I said, the 0.03 to 0.02 connection resistor will be determined later by experimentation. Here are the oscillation loop resistors in place. 510K between the 2 0.02 microfarad caps to ground. And here we see it, 510K between the 2 0.02 microfarad caps, and it's going to ground. The other resistor is the 1.5 megohm, and that's between the 0.02 and pin 1 of the 6BM8 tube, and it goes to ground also. And the one that should be between the 0.03 and the 0.02, remember we were not told the value, so that will remain for a later time when I can determine its value by experimentation. Just a quick pan here of the workbench to show you that no matter what kind of mess you've created, there's worse out there, okay? And here it is. I have no idea what kind of a slob has been working on this bench, but I hope to God they stop and clean things up. And on the cat updates, here's little Casey doing what she does best, which is take really long naps, about 24 hours a day. Bear in mind, back when she showed up on the doorstep and we adopted her, the vet estimated her age at like 8 to 10 years old, and that was 8 years ago. So she's probably like 16 to 18 years old, but still very active, and she loves some good scratch on the neck, and she's still doing great. Okay, so I Figured you'd be glad to see her and hear that. Now it's time to install the 500K reverse audio tremolo speed potentiometer. And because there is no intensity control, it has a piggyback on-off switch which will turn off the tremolo and on, and then we can adjust the speed with the pot. And let me show you how that is going to be configured. Here is the 500K reverse audio pot, okay, that I ordered from Antique Electronics Supply. Also, I had on hand, and I think I got from them originally, these piggyback switches that fit onto the back of the alpha pots, and all you do is uncrimp the little retention arms, take off the back cover, and then install the piggyback switch, and then you have your on-off capability and your speed control through rotation of the potentiometer wiper. There's the back cover removed, and then we will simply replace it with the piggyback switch. Also, you could make this into a foot switch if you wished. Okay, I don't tend to use foot switches that much, so I'm just going to go with the on-off on the control panel. But like I said, run a shielded cable out somewhere and make a foot switch that will either provide continuity or open the circuit to turn your tremolo on and off. And there you have the on-off switch piggybacked onto the 500K reverse audio pot. Tremolo off, tremolo on, speed control. Then I install the tremolo on-off and speed control in the control panel with the dial indicator and the 50% speed aiming vertically upward. So now the final step in the tremolo oscillator circuit will be to run a wire from the junction of 0.02 and 0.03 microfarad oscillator loop caps through an unknown resistor to the wiper of that tremolo speed control that we just installed. Now let's look down here. We see that that junction of the 0.03 and 0.02 is right here. So we'll be running a wire from this junction up to the middle terminal, which is the wiper of the speed control. But also we have to put the unknown resistor in series. I decided to complete the tremolo oscillation loop as far as I could. And so here, from between the 0.02 and 0.03 microfarad caps, I run a shielded cable up to a newly installed terminal strip. The shield is grounded to this terminal, and I have connected it to our distributed star ground. The signal then will be right here, and you notice there's a gap between the two terminals. There's no connection. That's where the mystery resistor, once it's determined what value is appropriate, will be installed. Then the oscillator loop signal will be sent up through another shielded cable to the center lug or wiper of the 500K tremolo speed control pot. The output then will come from this outer lug over here to one terminal of the normally open on-off switch for the tremolo. Then the other end goes to ground. So while the switch is in the off position, there is no ground provided to the oscillation loop, and that will stop it. It appears that the mystery tremolo loop resistor is a mystery no longer. While perusing the GA1RVT circuit that I discussed in the prologue to the Part 2 video, I noticed that the tremolo circuit was absolutely identical to the one in the RVT that we're building, and that the mystery resistor was labeled 68K. So let's assume then that that's the appropriate value for the resistor in our circuit, and let's install a 68K resistor closing the gap between the input and output shielded cables going to the wiper of the tremolo speed control. So now our tremolo speed and shutoff switch wiring is complete. Let's pause our amp building chores for just a few moments to acknowledge the receipt of a really nice gift from Ben Nelson, some guitar picks, a wrench to tighten the pilot light on Fender chassis. Now this is something long overdue, because otherwise without this it's a nightmare. Beef jerky for your old uncle, and greenies for the kiddies. So I think you covered all the bases, Ben, and I just wanted to say thanks from all of us. Now that the tremolo circuit is completely wired, let's turn our attention to the control panel and the input jacks. Well, the control panel's coming along nicely. We've got our high gain, low gain inputs, volume, tone, and tremolo speed, pilot light, and our on not on switch. Now it's time for the reverb intensity, which is going to be the 2 meg pot that I constructed from 2 1 meg pots. I'm sorry to report that using 2 1 meg potentiometers linked together to make a 2 meg will work as far as making it a variable resistor, but it does not work as far as a potentiometer. The resistor has 2 terminals, potentiometer has 3, so it won't work. But I was digging through the bin of ancient potentiometers, and lo and behold, I found a lovely 2 meg, and I have lubricated it, cleaned it all up, and it sweeps real smoothly and nicely, so I'm going to use this. Now, if you all are trying to find the parts to do this build, I understand Weber that sells the kits, that they may have a 2 meg available. Otherwise you'll have to hunt one down or use a 1 meg and hope for the best. Okay, I'm sorry, but that's the update. I'm going to change over to this jewel here for our reverb intensity. Now that the jacks and pots have all been installed, I have connected a ground wire to the rear shields of each of them, and then run it over to our signal ground lug that's welded to the chassis. Also notice that all the terminals are pointed down so they're closer to the circuit to allow for shorter length of wire to reach them. Here's another view of the potentiometers installed and grounded with the new 2 meg vintage pot in place. Now that the input jacks are installed and the shield lug of each has been grounded to the welded lug for signal ground in our chassis, it's time to turn our attention to the wiring of those input jacks, and step 1 will be the connection of 2 47K grid blocker resistors to pin 8, which is the grid of our 6 AN8 preamp tube. I've connected the 2 47K grid blockers to pin 8, which is the grid of the 6 AN8A, and now it's time to create the shielded cables that will carry the signal from the input jacks down to their respective grid blocker resistors. Here's an example of one of the shielded cables. At this end I have extracted the central signal wire and stripped maybe 3/16 of it, and then held the shield back with heat shrink. If one strand of this shield touches this signal wire, your amp will be dead. So you have to be really careful. Down here I have separated the signal wire from the shield. This will go from the jack signal leaf to the grid blocker resistor. This will be attached here to where the jack is grounded. You only ground the shield at one end, otherwise you'll create a ground loop and you will inject noise into your circuit. And this right here is the most sensitive wire in the whole amp for doing that. So you ground your shield only at one end. There you see the two shielded cables, one from each input jack to their respective grid blockers, and then finally to pin 8 of the 6AN8 first preamp 2. And now it's time to wire the high and low gain input jacks. And I warn you, as simple as this looks, I personally think this is one of the trickiest parts of the wiring in the entire circuit. And I'm going to try a different approach. Instead of going through this and showing you on the schematic and then wiring in the chassis itself, I'm going to go through and systematically draw a layout diagram that reflects what the schematic is trying to say. Okay, I'm going to translate it from this to a actual graphic representation of what these jacks will look like when they're wired in the chassis, and we'll do it step by step. As I said earlier, I'm going to try every trick in the book here to get you to be able to look at a schematic and then translate it into an actual wired circuit. Okay, so let's get started. Now, although I've already showed you the green grounding wires in the chassis going to the jacks, and also the shielded cables that will connect the 47K grid blocker resistors to the signal leaves, let's start from scratch with our layout diagram and see if it doesn't make good sense to you. Here's my diagram of the input jacks. We'll have the high gain on top, low gain at the bottom. They're not interchangeable. The way I'm going to show you how to wire them, they have to be high on top, low on the bottom. Terminal number 1 on each of them will be the shield terminal, and that, as you see right there, connects to the actual the barrel, the steel barrel in the center of the jack. That is what grounds the shield of your guitar cable. Pin number 2 here on both of these is the grounded leaf. That's that little short leaf that touches the big tall signal leaf and grounds it when nothing is plugged into the jack. Number 3 is the signal leaf, the big tall one that sticks up and actually makes contact with the tip of the 1/4 inch guitar cable jack. Now that we have our orientation and symbolism down, let's start wiring this. Number 1, the green wire that we're using for our chassis grounds will connect to the pin 1 on both jacks. Okay, and that is the green wire that is going to be connected to that chassis welded signal ground. So both of our shields are totally grounded. Here you see on the schematic, shield, grounded, shield, grounded. Now let's wire the shielded cables that are going to connect the 47K grid blockers, which are both connected to pin 8, which is the grid of the 6AN8 tube. We're going to have shielded cables that will connect those grid blockers to the signal leaf on both of the jacks. And here I've drawn shielded cables from each of the 47K grid blockers up here, and the central shielded wire is connected to pin 3, which is that tall signal leaf in the jack. It's the same on both the high and the low gain input jacks. Okay, so the central wire is connected to leaf 3, and then a wire from the shield comes over here and goes to chassis ground. So the shield is connected to chassis ground, and there is no contact between the central signal wire and the shield, or else you will short out your signal and have no sound at all from your amp. Now, believe it or not, is where things are going to get a little tricky. We're going to run a wire from the ground leaf, that's number 2 of the low gain, up to the signal leaf, which is number 3 of the high gain. So here we go, from number 2 of the low gain, that's the ground leaf, up here making no contact with anything, up to leaf number 3, the signal leaf of the high gain jack. Next step's an easy one. On your high gain input, just run a short wire between number 2, the ground leaf, and number 1, the shield or grounded leaf. That's on the high gain. Here we see the connection between the grounding leaf, which is number 2 of the high gain jack, and ground, which was the number 1 or shield or grounded leaf. In the final step, we're going to insert a 1 meg resistor between the signal leaf of the high gain input jack and chassis ground, which can be this grounded leaf here, which is connected to the chassis ground. And here we see the connection between the signal leaf, which was terminal 3 of the high gain input jack, through a 1 megohm resistor to ground, which was the number 1 terminal or a shield or grounded leaf. And here's a simple test that will give you a pretty good idea if you wired your jacks correctly. Remove the housing from the back of a 1/4 inch jack. Connect an ohm meter across the 2 terminals. And in this case I plugged into the low gain, which remember was going to have 47 plus 47, or about 94K of impedance to ground. And sure enough, I have 93.9, which is about as close as it. Now we'll unplug this and insert it into the high gain receptacle and see if we have about 1 million ohms of impedance to ground. There we are, plugged into the high gain receptacle, and we see that we do indeed have 1.04 megohms. So it would appear then that the 2 input receptacles are wired properly. Well, that's about it for the construction of our layout diagram of the input circuit of our Gibson RVT amp. I can't think of a sub-circuit that more clearly demonstrates the lack of any resemblance between schematic and reality. But as you watched, I made a translation from this to this. Okay, now what I would offer this to you is this is a nice intermediate step for those who have a hard time translating directly from schematic to the hard wiring in your amplifier circuit. If it helps you, then convert your schematic to a layout diagram like this. Draw your components where each of the contacts is going to be so that this is a pretty good sketch of reality of what the circuit will look like in the chassis. Then go back and make your connections based on what the schematic tells you. Then once you have this layout diagram constructed, not given to you, really as it was in this case, but in future cases, once you constructed your own layout diagram, then you will have an easy time converting this to the hard wiring within your amplifier circuit. Eventually, you will be able to translate directly from this to your amp circuit. But meanwhile, drawing this will greatly enhance your comprehension, your three-dimensional visualization of how the schematic is going to appear once it is constructed in the chassis. And if you're wondering why I didn't use my own input jack wiring as a demonstration, it's because due to the way I label the chassis, mine is upside down from the schematic and from the layout diagram that we constructed, and I thought it would be really confusing. Okay, so I'm afraid our fourth feral cat update has some rather sad news. It involves Ollie, who we took care of in the backyard for like 6 or 8 years, and then she decided to move into our garage about 4 years ago and lived there quite happily. And she passed away, I'm sorry to report, fairly recently. We think from natural causes, probably associated with her age. Okay, but she's now buried in the backyard right beside Rusty, and I'm sure that they're keeping an eye on each other and keeping each other company. Okay, so let's watch a video that I made of her just before she moved into our garage, and have our fond recollections of a really great little pal and fine guitar player, Ollie the feral cat. Well, it looks like our vagabond feral cat has returned home. She must realize that it's time for some audio demonstrations. So here's Ollie. She's probably just got up from her cat nap, and it's really hot. You can tell she's kind of breathing through her mouth, but she's begging for food, which we will gladly provide. Hey Ollie, it's like Wild Kingdom here. Yeah, you're a good girl. You hungry? Ollie? Yeah, she's hungry. She's always hungry. So let me set down the camera and go in and get her something to eat. Come here, girl. Good girl. Now let's take a look at the negative feedback loop. We connect to the speaker output signal. I've gone to the 8-ohm jack. We come over here to the center lug of a double pole double throw switch. It doesn't have to be double pole double throw, but that's the only micro switch I had on hand, so I used it. And I've run the signal to the center lug, and then I've done a jumper from left and right over here to the one end of the 47K resistor, and then the other end of the resistor runs down here to the cathode, which is pin 4 of the 6EU7. Let's look at it here on the schematic. You see here we come from the signal output to the speaker through the 47K resistor, through our negative feedback switch, and down here to pin 4, which is the cathode of the 6EU7. The 6 BM8 tube is completely wired except for the filament supply. So I think it's time to run 2 tightly twisted green wires from these 2 terminals which is where I parked the 6.3 volt supply from the power transformer, run the twisted pair over here and to our pins 4 and 5 of our 6BM8 tube. Now this is one of the more, frustrating, miserable tasks in all of amp building. But I have kind of my own way of doing it, and let me explain that to you and see if you like it. I cut 4 pieces of wire that are at least long enough to reach from the 2 terminals where I parked the 6.3 volt supply from the power transformer, and they have to reach from those terminals over here to pins 4 and 5 of the 6BM8 tube socket. Then you strip the ends, twist them, solder them, and crush the solder joint with a pair of pliers so that it's like a flounder, okay? Thin from one side, wide from the other. Why? I'll show you in just a second. The slots on tube socket pins are narrow but tall. So we want our pair of flattened wires to be able to fit successfully into this oval hole and then be soldered. Now looking in here, you'll see that the flattened soldered joint fit nicely through that oval slot on pin 5. Now we'll do the same thing on pin 4, and then we will solder the wires to the pins. There are the 2 pairs of green 6.3 volt filament wires soldered to the pins 4 and 5. Now we're going to take 1 wire from each pair and twist them tightly, bring them over here and solder 1 to each of these 2 terminals, joining them to the 6.3 volt output from the power transformer. And there we have a nicely arching 6.3 volt filament supply to the 6BM8 tube, and you already have the wires to continue on to the 6EU7 tube. All you have to do is twist them, cut them to length, and solder them to the socket. Okay, so also it's best to have them arch up and come down into the tube. You do not want these wires laying around on the floor of the chassis or wrapping around the tube base. This is the best arrangement right here. Also, we know that because the center tap is grounded in the 6.3 volt supply, that the AC in each of the wires is out of phase with the other wire. By twisting them like this, their electromagnetic fields cancel out, and we can essentially eliminate any chance of AC hum. Now it's time to finish wiring the 6EU7 tube socket. It looks like pins 1, 2, 3, 5, and 7 have nothing connected to them. So let's take a look at the schematic and see if we can figure out what needs to be done to finish this tube socket. Well, pins 1 and 2 will be our 6.3 volt filament leads. 5 is the input to the grid from the volume and reverb intensity controls, and 7 will be the plate power supply through a 470K plate resistor. Okay, so let's tend to that. Let's see here which we can wire first. Let's do pin 7. Looking at the schematic, we see that there is a junction of a blue wire and the 330K resistor to pin 6 of the 6EU7 triode. We need to find that junction and then put in a 470K resistor to pin 7, or the plate of the other triode of the 6EU7. Let's see if we can't find that junction. Well, it's kind of hard to see, but there's the blue wire. There's the 330K resistor, so we're going to run our 470K resistor from this junction of the B plus and the 330K resistor. We're going to run it from here over to this terminal, and then we'll run a wire from this terminal down to pin 7 of our 6EU7 tube socket. Alright, here we have our 470 ohm resistor from the blue wire carrying B plus over here to this terminal. Then we run another blue wire down here around the tube base and into terminal 7. This wire now provides the B plus to the plate of the triode as well as the plate resistor. Alright, here we go. We're starting at pin 7 of the lower triode, and we go through 0.02, 1 meg, and then we go into pin 5, which is the grid of the upper triode. Okay, right at the tip of the stylus, pin 7, we go through the 0.02 microfarad cap. It curls around and comes over to this terminal, and then we go through the 1 meg resistor down here to pin 5. Now I've also taken a wire off of pin 5 and parked it over here on the terminal strip because we're now going to wire our volume control and our reverb intensity and eventually our 6 and 8 tube. Now we can finish wiring our 6EU7. We have pins 1 and 2, which will connect to our 6.3 volt filament supply. Pin 3, we're going to get off easy. There is no connection. It's not used, so we'll just leave it as is. And there's the continuation of the 6.3 volt heater supply to the 6EU7 tube pins 1 and 2. And also notice, as I showed earlier, I've already connected the wires that will continue on to the 6A and 8A. Now it's time to wire the 6A and 8 triode, and we already have a blue wire running to the plate, which is pin 1, from our reverb driver transformer. We see it right there. Next, we have pin 2. Now that is the grid of the tube, and it receives the signal from the amplification stages through the reverb intensity control, that 2 meg pot, where either more or less of the amplified signal will be sent down here to drive the reverb tank. So we need a shielded cable from pin 2 up here to the wiper of the 2 megohm reverb intensity control. And here we have it from pin 2. You see the shielded cable come up and connect to the wiper of the 2 meg reverb intensity pot. The shield is grounded to the back of the pot, that rear metal cover, and all of the covers are connected to the distributed chassis ground. Okay, so that's completed. I should also say, if you're wondering what this shiny black substance is, it's some black silicone sealer. I'm using it to reinforce the connections because the central shielded wire is quite small, quite thin and weak, and so I think a little reinforcement here to cut down on motion and vibration would be a good thing. Pin 3 is a 1K bias resistor to ground, and we see in here pin 3, 1K bias resistor to ground. Now this is higher wattage than is necessary, but it's the only one I had on hand. Now for the plate supply of the 6AN8. Recall that I added a 10K internodal resistor and a 10 microfarad filter cap in addition to what the schematic specified. So this is in the doghouse, and I'm going to run a wire from the capacitor down into the chassis. It's going to be through a 470 ohm plate resistor, and it will go to pin 6 of the 6AN8 pin. Here it is. Now the previous B+ wires have been red, white, blue, very patriotic, and black. So let's see where the black wire goes inside the... Now I get pretty sneaky with this one. You see the black wire coming through the grommet. I ran it behind both of these terminal strips and then soldered it right here at the last terminal. So we're going to go from this point to finish our plate supply for the 6AN8. Here we see that black wire from the power supply on the back of the chassis coming up here, and it's going to branch to 470K to pin 6 and 1.5 meg to pin 7. And there is the terminal that I connected the black wire from the power supply to. And we see here that we have the 1.5 meg ohm resistor going to pin 7 and the 470K resistor from the B+ to pin 6. Now from the junction of the 470K resistor and pin 6 of the 6AN8, we need to run a 0.02 microfarad capacitor. This will be a coupling cap to the volume control and to the reverb intensity control. Here is the pin 6 junction. I have added a 0.02 microfarad coupling cap, which goes around back there with a green insulator, comes up to this terminal point right here. Then it goes through a shielded cable up to a new terminal strip that I just installed, and from this point right here where the signal is, we're going to run a 1.5 meg ohm resistor up to the wiper of the volume control. As you can see, that's right here, 0.02 microfarad cap. This will be a shielded cable, 1.5 meg ohm resistor to the wiper of the volume control. After that, I will run a shielded cable to this end of the reverb intensity control. Now that the 6ANA tube socket has been completely wired, it's time to install the twisted 6.3 volt filament supply to pins 4 and 5. Here we see the 6.3 volt filament wires tightly twisted to D. Snyder specifications, then securely soldered to pins 4 and 5. Now with that deft move, we have finished the wiring of the 3 tubes in the amplification circuit and all of our controls other than the tone control, which, as you recall, I've added to the circuit. So let's discuss what type of tone control we're going to use and how we're going to insert it in this circuit. Well, I've decided for the tone control to use a very basic one from the Fender 5F2A Princeton. And you see here is the tone control. This is the volume control. So let's see how we're going to wire. Okay, let's start off here from the wiper of the volume control. We'll go through a 0.0005 microfarad cap into the tone control. Here's the wiper. I go through a 0.0005 microfarad cap into the left terminal of the tone control. Next, from the junction of the 0.02 microfarad cap and the volume control, I will go directly to the wiper of the tone control. Well, here is the 0.02 microfarad and volume control junction, so I'll run a wire from here over to the wiper of the tone control. And then finally, on the right hand terminal of the tone control, we go through a 0.005 microfarad cap to ground, and we see here that that is the right hand terminal. We go through the 0.005 microfarad cap up here to the signal ground that is connected to the shell of the tone control pot. And with the installation of this final wire, we have completed wiring the circuit for our GA1 RVT Gibson. Now though, rather than hastily just plug it in and hope for the best, I'm going to go back over the entire circuit and compare every single wire, joint, component value and everything with the schematic to make sure that I have made no errors in the construction of this circuit. Well, I'm back from an exhaustive review of every single connection, wire, and component in the circuit, and in the spirit of full disclosure, I will admit I made two mistakes. Number one, I didn't solder this connection right here. Okay, and number two, I forgot to install the 0.047 microfarad cap between the screen grid and ground. And there it is right there. It is now installed. And I believe that the circuit now is ready for us to continue with our evaluation and eventually testing. Well, I got brave and put the tubes into the mighty GA1 RVT, plugged it into the current limiter, and switched it on. The plate to cathode voltage on the 6 BM8 is only 285 volts, whereas the schematic specifies about 265. So we're about 20 high, and that's probably due to the higher AC wall supply that we have now. Also, there is a hum that you can hear, but I think it has to do with the fact that the shielded cables are not installed on the reverb CBS jacks. When I touch and disrupt it a bit, it's almost dead quiet. So I think that is probably not a real issue. So let's go ahead and continue with our troubleshooting and investigation of the effects of the amp. Also, I need to calculate the plate dissipation on the 6 BMA to be sure that it's not going to go up in flames. Okay, I measured the resistance of the primary of the output transformer. It's 381.5 ohms. And I measured the voltage drop across the primary when the amp is operating, 11.25 volts DC. When I divide the voltage drop by the resistance, I get 29.5 milliamps, and the plate to cathode voltage or plate voltage is 285 volts, which gives us a plate dissipation of 8.4 watts. Now when we look up our plate dissipation value for the 6 BM8, we get code C. We look down here at plate voltage less than 250. maximum PD is 7 watts. At plate voltage greater than 250, maximum plate dissipation is only 5 watts. Well, that's kind of upsetting. We're at 8.4, okay, which is higher than either of the recommended maximums. So let's give a little thought about how we can bring that down. And you can see here in the normal operating characteristics, they speak of a plate voltage of 200 volts with about 35 milliamps of plate current. So 200 times the 35 is going to give you the 7 watts that they recommend as the maximum. Okay, we're at a much higher voltage and a lower current, but not quite low enough. I guess we've got to reduce our plate current a bit so that we come into the, or within the 5 watt limit on plate dissipation. I plugged in the reverb tank with the shielded cables just to see if that's what was causing that hum, and the hum went away. Dead quiet now. Let's see if we have any reverb. I'm going to bounce the tank. There. Wow. Sounds like we have reverb. Next we have to test the tremolo. Okay, I'm injecting a 400 hertz input signal, and let's see if the tremolo will tremulate. Remember, it has that piggyback switch. I'm going to switch it on. Wow. Nice speed control. And the switch shuts it off completely. You really need the switch, otherwise you're going to have that going all the time. Okay, I'm really excited. And the tremolo, I was warned, would thump loudly since we're going into the grid of the output tube, but it's really nice. I don't hear any problems with it. And bear in mind that the reverb is working. And of course we have some fine tuning to do and all, but as it stands right now, I'm dangerously close to pronouncing this a success. Okay, there's still more testing and troubleshooting to do, however, so stay tuned. Well, I'm so excited by how well the amplifier works that I'm actually going to do the unthinkable and clean up this god-awful mess that I've created here, hopefully before the city condemns my workshop. And then we can start over tomorrow with a nice clean space, and we can optimize the circuit of the mighty and elusive Gibson GA1 RVT. I feel like this is an opportune time to bring this part 3 video to an end. As we've seen, the amplifier is fully operational, but I'm going to warn those of you who are working along with me on this that in part 4 we will see that there are at least 14 modifications to the circuit to optimize the performance. So you might want to wait until you've watched part 4 and possibly incorporate those changes into your circuit if you feel that they are appropriate. And for the rest of you, let me only assure you that part 4 I think is really going to be special. I think you'll be amazed by the quality of the tremolo, the reverb, and the overall tone of this little amp. Okay, so please stay tuned. Part 4 is already well underway and should be posted, I'm going to say, in probably 2 or 3 weeks. Okay, so I'll see you then. Meanwhile, I wanted to take a few moments to thank all our Patreon patrons and PayPal contributors for keeping us on the air and advertising free for another month. If you would like to join them in the support of our ad-free channel, I will put links in the video description that will assist you to do so. Okay, so thanks for watching. As I said, stay tuned, and we'll see you again soon. Bye for now.